This is Sholey Physics, episode on force on a conductor. In the last couple of sessions, we've been talking about how a charge moving through a magnetic field experiences a magnetic force that causes it to change its direction. So today, we're looking at moving charges through conductors and the effects that that has on a conductor. Right here I have an apparatus. It's just some bars here, metal bars on either side. And there's this movable rolling bar, and if I tilt it a little bit, you can see that there's a couple of magnets here stuck quite well on there. There's one on the bottom, one on the top, and they're oriented so if I put them close together, they would attract together. So there is a magnetic field either going from top to bottom or bottom to top. I'm not real sure about that right now, and I could probably figure out in a moment. When I put this bar in the middle, between those magnets, nothing happens. However, when I connect a battery up to it, I'm going to connect the other end to that side. There's a current that's going to flow through that wire, and it starts to roll. Now, just to show you that there's no tricks, no weapons here, I'm going to put that back and switch the polarity. And what do you think is going to happen now? It rolls the other way. All right, so there's a force that's applied to this bar that's very observable here. You saw that current go up. I have a ammeter hooked up to check out the current. So this is the force being applied to a conductor as the charge moves through that conductor, and the conductor is in a magnetic field. Very practical application of F equals QV cross B. Well, today I'm going to show you where that comes from. Is actually coming directly from that F equals QV cross B equation, but we're going to put it in terms of current, electrical current. All right, so starting off with that expression. Been our theme of the last few sessions. We're going to set up a couple of bars, conducting bars in the sketch. I'm going to put a movable bar across them, and we're going to hook these up to a battery. There it is. All right, so if I take that bar away, there won't be any current flow. If the bar is there, there will be a current flow, and the current will be flowing in this direction. So we have it defined. Now right now, nothing's going to happen in the bar because we're missing something very important. We're missing that magnetic field. So we need to put in a magnetic field here. Try to make this uniform, evenly spaced field. So this magnetic field is pointing up out of the paper. That's its direction. And of course, magnetic fields are always yellow. There we go. All right, so if we're counting on positive charge moving from the positive side of the battery to the negative, that's the direction of our current flow. Then positive charges moving this way across the bar, what's that going to do to the bar that's movable? Which way is it going to force it? Well, if charge is moving up this way, and we turn our hand towards palm side towards the direction of the field, so my fingers now bend toward that field, the force is going to be to the right. So there will be a force on this bar in that direction. Okay. If we reverse the polarity, the force would be back in the other direction. It would be a charge moving this way with our magnetic field up, so the force would be to the left. So there we have it. But in terms of current, what would the force be? How much force is on this bar? It's not too difficult to work out here. You see, if we take a little segment of this movable bar, infinitesimally small, tiny, there's going to be a little tiny force on that segment, dF. We'll zoom in a little bit there. Okay, little tiny force, dF, on that segment of the bar. So what would DF be in terms of all these other pieces here? Well, that little segment DF would also have a little segment of charge DQ moving through it. All right. So this Q is not the whole charge from the whole body of the bar, but the charge from just that little segment. So we'd have a little DQ thrown in there. All right. Well, the next piece, zoom out a little bit. There we go. The next piece of it, we've got V. Now V is the velocity of the moving charge. If this were just a single charge, like a proton moving through the bar, it would be the velocity of the single proton. But in this case, V is a rate. And what we want to think about here in terms of is current. You might also recall that current is a rate of charge. So if we plug in velocity's definition of a dx dt, right? A rate, an instantaneous rate of change in position. We keep that as our vector, and we'll keep that crossing with b for now, okay? We have a big mess here, don't we? But wait, let's simplify this a little bit. You see that little df should just be the collection of force of all the little pieces of that bar, all the little pieces of length of that bar. And if we rearrange these two dq dt's so that they're together, we've got the dq dx over dt. If I bring this dt over to be with the paired up with the dq instead, look at what we have. Look at that. See, now we have this quantity dq dt. You may recognize that as the electrical current. And now we're left with dx cross b, the magnetic field strength. I guess I should label that up there, shouldn't I? There we go. Labeled. And so if we sum up all of the force for all that length, what are we going to get? We're going to get the entire force. The net force on that bar is the sum of all the forces. Look at that. Equals I. And here we'd probably summing up from 0 to the length L. Now L, I should probably describe here. Is it the length of the bar? No, not in this case. If you look carefully, what's the length, the distance that the current is going to travel? It's going to travel from here up to here. So we're going to define that as L, the length. Okay, length of that bar, length of that conductor. So when we sum this up, integral of dx is just x, and we're going to take that from 0 to L as our upper and lower bounds there. So this integral of dx just turns into an L cross b. Now, what is a vector L? Well, this would be the direction of the conductor, the direction of the length of the conductor, and we're also going to use the direction of the current flow. Okay, the direction of the current flow is going to give it the direction. So the length of the conductor is the magnitude, and the direction of the flow is the vector L's direction. Now I used a capital L. You're more commonly going to see this as the force is I lowercase l cross b. Now we're going to go to the more common way to remember this. Okay, my good physics pal, Mr. Shearer, enjoys calling this by a name, particular name. You see, if you take L cross B, consider that the cross product there gives us a sine of 90 degrees. As long as the current is perpendicular to the magnetic field, then we'd have a ILB sine 90. And of course, sine of 90 is 1. So here you get that magnetic force on a current carrying conductor. Its magnitude is equal to ILB, or if you put it into a different order, BIL. In other words, force equals Bill, F equals Bill. And you get the magnitude of the force on that current carrying conductor. Okay, so if we look at this, we can probably determine the direction of this magnetic field. Zoom back out here. Right now I have the red wire connected to the positive side of this battery, and I'm going to hook up the yellow wire to the negative side. Okay, let's see which way it's forced. That's forced outward. Look at that. So with the positive side going in this way, we got current going this way, and it was forced, the bar was forced this way. So is the magnetic field going up out of the page or down into the page? What do you think? Well, if we take our right hand, we get a force going like this. The current's going to be going from the bottom down here to the top up here, from the positive side to the negative over here. So the current flow is this way, and we get a force that way. So the magnetic field should be down. So therefore this top magnet should have its north side facing down, and the bottom magnet has its south side facing up. Look at the polarity of those magnets. There's a little offshoot application, but that's our F equals Bill presentation, our force on a conductor. More to follow, including a lab. See you later.